What we're now going to talk about is a device that enables us to examine the emissivity of different surface finishes, and it is referred to as being the Leslie's cube, or a Leslie's cube. So this is a device that was devised by a fellow named John Leslie in 1804. What the Leslie's cube consists of, just like it sounds, it is a cube. So it's a cube made out of copper, and in the top there's an opening, and it enables you to pour a liquid into the cube. So this is made out of copper. Could be made out of other materials as well, but that was the one that I had, was made out of copper. And then what you do is you put hot water into it. And each of the sides of the Leslie cube have different surface finishes. And so the one that we'll be looking at in a short while here has, one side has white paint, the next side has gloss black paint, then the next side has flat black, and the last side is just bare copper. So if you recall, when we were talking about radiation, we said that there's a black body, an ideal black body radiator, and for that we had an equation that enabled us to calculate the amount of radiation emitted from that type of object. And so the radiation emitted on the right was watts per meter squared. This is the Stefan Boltzmann constant. And then this here is the surface temperature in Kelvin. And this is actually integrated over a broad range of wavelengths. The actual amount of radiation is wavelength dependent, but this equation would be integrated over all wavelengths. Now, it turns out that we had talked about how real surfaces do not emit this full amount of radiation. They actually emit a little less, and so a real surface emits with the following equation, and here this is the emissivity. So that is the basis of Leslie's cube. It enables us to study that. So what we're going to do, we're going to take a look at a video of a Leslie's cube with hot water inside of it, and we'll take a look at what results when we look at that with an infrared camera. So here we go. So what you're seeing here is an image. The IR camera is up on the left. Visual is straight ahead. So we go from white to gloss black, flat black, and then we get to almost like a polished copper finish. And we go back to white. And so the IR camera in the upper left corresponds to what you're seeing in the middle image. So that is what the IR camera is collecting. Now we can analyze that data because with the IR camera we do get temperature data. But what I did is I put a thermometer into the Leslie's cube, and there you can see with white it's 40.8. Now the thermometer is right in the middle of the liquid, so it's not going to change. But all of the surfaces should be reading at about 41 degrees Celsius, as we can see from the thermometer. And so all four of the surfaces should be reading that on the Leslie's cube. But now let's take a look at what happens when we go to the IR camera. And so this is the first image from the IR camera. And this would have been for the white surface finish. And then we go to the gloss black, 41.7, so that's not far off from what we'd expect. 41.2 for flat black. And now the last one is going to be copper, 27.5 degrees C. So what is going on there? Well, that is a perfect demonstration of the idea or the concept of emissivity, because what we saw was that for white, gloss black, and for flat black, the temperatures measured with the IR camera were all pretty accurate to what we had with the thermometer. But then when we went to the polished copper finish, it was 27.5 degrees C, very, very different from the 41 degrees C that the water inside of the Leslie's cube was at. And what is going on there is the fact that polished copper has much different emissivity from the painted surfaces. So let me write out what the emissivities are for the different surface finishes that we just looked at. Okay, so there we have the emissivities for the different surfaces, and you can see for all of the painted surfaces that we looked at, the emissivities are all pretty close, 0.93, 0.92, 0.94. Now that was for an oil paint. I'm not exactly sure what finish it was on the Leslie's cube, if it was an oil paint or other, but that's irrelevant. The paint was similar to values that you look at for emissivity. Paint typically around 0.88 to about 0.95. And so those were the values of the emissivity. That means that it's emitting most of the black body radiation value. Now when we look at copper, however, polished copper, really, really low emissivity, and consequently that's also why we were measuring kind of a very low temperature with the IR camera. I think it was around 27 degrees C when it should have been around 41 degrees C. Now, I didn't have perfectly polished copper for the cube that I showed you. It was kind of old and a little tarnished, so the emissivity may be a little bit higher than this 0.03. But you can set emissivity in any kind of infrared detector. And the camera that I was showing you the results for, the emissivity for that camera is set to be 0.95. So what does that mean? What that means is that if you wanted to use an infrared camera to measure the surface temperature of an object, you need to know what the emissivity of that object is. And so if you're measuring something such as copper, polished copper, chances are you're going to get an incorrect result if you do not adjust the emissivity accordingly in order to correspond to whatever the surface finish of that copper would be. So anyways, that is a demonstration of emissivity, and it shows us the importance of knowing emissivity values for our engineering calculations, because if we're off with the emissivity, our results could be very, very incorrect. And consequently, we do need to pay attention to emissivity when we're doing our calculations. So